Okay, we're going to take a look here at example number 1 and start to see how exactly this problem can be done. So this is the same issue with the same problem with the strength shoes and people jumping. So we're going to say this extra part at the bottom. At a 10% level of significance, is there enough evidence to support the manufacturer claim, which is that athletes can increase their vertical jump heights using the new strength shoes? We're going to assume that vertical jump heights are normally distributed. We already kind of wrote down in the previous video what these different hypotheses would be. So I'll just recopy them down here and we'll talk through them again. Keep in mind what these hypotheses represent. And sometimes it's helpful to write down what this means in words. Remember that if there's a difference between these values that's positive, then that meant that there was an improvement, that the shoes actually helped. And if I got a difference of 0, that's kind of like person number 3. That means that there is no improvement. There's not a loss of improvement or anything. It's just no improvement. Okay, so these are kind of what I'm deciding between. And I'll really very often encourage you in this section to write down in words as well as symbols kind of what your hypotheses actually mean. Okay, so for our test statistic, we're going to start to write out our evidence. And there's not much evidence to be written here. We have a number of differences that we can form, which is going to be 8, because we have 8 athletes that we were working with. We can also see that we should enter our data into lists. And we kind of already did that, so I don't need to go through and do that here again. For the checks, I know that I can go and take a look at the formula sheet to see what check I need to run. So on the formula sheet for a hypothesis test, I'm told that I need to check that my n is greater than or equal to 30, or that my samples come from normal populations. In this question, though, we said assume vertical jump heights. Assume vertical jump heights are normally distributed. So we kind of already have that, which is great. So we can check that off and we know we're ready to do the t-test. The only thing we have left to write down is what our t-score is, and we'll do that as we complete the next step. So remember right now, we have different D bars. We have kind of these improvements that we could get, this kind of average improvement. And what we've discovered is that right now, we believe H0, that we should expect to see an improvement of 0. But remember that the D bar that we got was a D bar of 1.75. And so we're wondering if that seems to be a bit too high. And so we'd like to be able to determine the p-value. Of course, that p-value would be calculated by getting a D bar that's greater than 1.75. And the calculator will give us that number. We can also label our picture with our t-score. T-score for 0 is 0. And we don't know the t-score yet for 1.75, but we can certainly find it once we run the calculator test. Remember that the calculator test we're going to run is a t-test. And I'm going to go ahead and say that I actually have data. This is the best part about running this test, is that once I have all of my differences in the calculator, I can just update this list to be whatever list had those differences in it. Notice I can't choose the list that has the before jumps or the after jumps. I want the one that had the differences, and that was my list number 3. Notice that my mu0, that's the number from the actual hypotheses. Couldn't find that word there for a moment. And down here, my alternative hypothesis said that I believe that the average is greater than 0. So we're ready to go all the way down now to calculate, hit the enter button, and see what we come up with. So it looks like I have a t-score of 2.3333. Makes sense because my value of 1.75 was above average. I get a p-value of 0.026. 262. And I can then start to see if that seems to be rare or not rare. my alpha value here was told to be 10%. So anything that happens under 10% of the time, we'll say is rare. So this does indeed seem like a rare sample. And so that means that we will choose to reject H0. It doesn't seem like a good fit here to say that this could have happened just by chance. So we'll say it is unlikely to get a sample average difference of 1.75 if the actual difference is 0. So therefore, we have enough evidence to believe that the average improvement for all people is greater than 0, right? That there actually was some improvement. If we're rejecting H0, we think H1 sounds like the better conclusion to reach. So this is a really, really powerful idea that we can go ahead and start to utilize now, that we can deal with these kind of dependent samples. Okay. One thing that I want to make sure that I show you before I let you try the next couple problems is that, again, if I look at what the t-test generates for me, I'll notice that in here, it actually does highlight for me my values of S and my values of X bar. And X bar is actually very significant because that's equivalent again to my D bar that I had over here. So I would know what number to put on my number line. And I know what number then also goes in my p-value calculation. Okay. So I'm going to ask you to go ahead and actually try to work on something like example number 2 and even example number 3. And the hardest part here is oftentimes setting up those hypotheses. But you can take a look at the solutions that are up online and tell me, or hopefully be able to work through them, and tell me any questions that you have via email or in office hours. We'll take a look in the next video at how we could actually do the same sort of thing using, again, a confidence interval.